So we're talking about, might seem a bit strange to have a Turing machine accept as input a string description of itself. And so that the string input W is actually angular brackets n, where the Turing machine that string is going into is itself n, right? And you've probably come across something similar, well, if not at least the following situation, by analogy, would seem plausible. And that's in the context of compilers. Now, let's see. So, remember, a compiler is just a translation program, right? It's a piece of software that translates one language into another language, usually a high-level English-like language into a very low-level binary language of zeros and ones that's suited to the computer, that the hardware, the logic gates can recognize. Okay, so a compiler is a translation program. Now, let's say the compiler is for the language Pascal. It's quite a well-known, fairly popular, well, it was, computer language. And what does it do? The compiler for the language Pascal. Well, it takes a software program that's written in the Pascal language and translates it into, well, something. That doesn't really matter what. Okay? Now, consider that this compiler, it's a piece of software, right? Imagine that the code that this compiler is written in Pascal. Okay? So that then opens the possibility that you could have two versions of the program. Which program? The compiler software. You can look on one version, and they're just two identical copies of the same program. The compiler. The compiler is just a program, and two identical copies. And you look on one as the program that's actually going to execute. It'll do things. And the second copy you look on is just data, right, as input to the first one. So now, since the second copy, the one that you're going to look on as data, since it's written in Pascal, then it's acceptable as input to the compiler, right? Because the compiler, what does it do? Well, it translates from Pascal into something else. Okay, so the second copy can serve as input, goes into the first copy, and that first copy is acting as a compiler, but the second copy is just acting as data. But it's the same program, right? So in other words, you have the first copy translating itself, in a sense, if you see what I mean. The first copy is acting on, it's translating, the Pascal program. That's the second copy. But that second copy is the compiler software. Okay? Might seem a bit odd, but that's quite acceptable. And it's something that can happen in the real world. So you can imagine a Turing machine being able to process an encoded version of itself, an encoded description of itself, what it does. Okay, so by analogy. All right. So hopefully it's not too weird a concept of a Turing machine having as input, the input stream is an encoded version of the description of itself. Okay? So the Turing machine M accepts as input angular bracket M, the encoded description of itself. Okay, right. So now let's move on a bit, and I'll show you where the paradox comes in. Because remember, we're still in the process of trying to derive some kind of contradiction, because we're in the middle of proof by contradiction. So we have to get some contradiction somewhere. So how to do that? Well, we're getting there. So a bit of summarising here. This D, the Turing machine D, that uses H as a part, a component, a subroutine, if you like. So what does it do? Well, it will accept. It's a Turing machine. It will accept. Now it does the opposite of what H does. Right? And what does H do? If H accepts this, in other words, machine M accepts the description of itself. So if H accepts, then that means the machine M accepts the description of itself. Right? And D will do the opposite. So if H rejects, in other words, M does not accept the description of itself, D will accept. D will do the opposite of what H does. Okay. Now, so that means that D will reject if H accepts, and H accepts if M accepts the description of itself. If you're confused by that, go look at the text, study this. We're talking about three machines. We're talking about D, we're talking about H, and we're talking about any old M, any old Turing machine M. Okay, D does the opposite of what H does. H accepts if M accepts this. H rejects if M does not, or if M rejects this description of itself. Okay, now here's the punchline, and I'm debating whether I should give the trumpet roll soon, just after this, or wait to the end. I think I'll wait to the end. Anyway, but here's the punchline. Here's where things get really subtle and funny, right? Okay. So D of angular bracket M is this. Okay. All right. What happens? A fascinating question. What happens if instead of M here, some random arbitrary M? See, D is a Turing machine. This is just any old Turing machine. What happens if we put D here? Because D is a Turing machine. M's any old Turing machine. So we could have D in brackets, angular brackets D. Right? We could have this. Well, here's the description for general M. Okay. So if we want to know how D of angular bracket D, how that's going to behave, well, we just take this description and we just throw out the M and put a D instead. Okay. Well, here it is written out, and watch what happens. Okay. So I'll say that again. So we're going to instead of an arbitrary Turing machine M, now we're going to put D there. So instead of M, we'll have D. So we'll have a D here, a D here, D here, D here. So here it is written out. But now, look. I mean, it sort of hits you. Like, so D of angular bracket D. So this D machine, it'll accept if D does not accept the description. Right? And it will reject if D accepts the description. Okay? Right? So that's That seems like a real contradiction, right? So whatever D does, it's forced to do the opposite. So so except if D does not accept the data of D itself, and reject if D